since we are going to compare two population means, what we will be doing technically is discussing the difference between two population means. And to do that, as always, we will use the sampling distribution that we get from a specific sample. So in this case, we will be discussing the sampling distribution of the difference between two samples means. And if you look at this graph, you can see that this distribution is normal, and the mean value of the difference between sample mean 1 and sample mean 2 is equal to the true population mean difference, which is right there in the middle of the distribution. And that brings us to the following three properties of the sampling distribution of two samples mean difference. So the mean of the sampling distribution, x1 minus x2, is equal to the mean of the two populations. And as for the standard deviation, it is calculated in the following way. So we take the square root out of population variance divided by sample size 1 plus second population variance divided by the sample size of, the population sample size. And we also assume that the sampling distribution of the difference between two sample means is approximately normal for large samples. So first of all, let's see how we can construct the confidence interval for the difference in population means. So when we know the true population variances, here is the formula. So first we calculate the difference between two sample means, subtract and then add a z-score at the critical level of alpha over 2 multiplied by the square root of, as we know, this is the standard deviation of the sampling distribution. However, as we already know, we almost never know the true population variances, therefore we have to work with their approximations, which are samples variances. So therefore, instead of using this formula, we will use this formula. So the second one, which is almost identical to the first one, the only exception is that instead of having sigma 1 and sigma 2, so the true population variances, we will have two sample variances. As before, z alpha over 2, this is the critical z-score at the significance level of alpha over 2, and alpha, this is the significance level specified a priori. We can also do hypothesis testing for the difference between two population means, and similar to the case of confidence intervals, we will have two possibilities: when we know the true population variances and when we do not know them. So when we know them, the z-score is computed in the following way. So first, in the denominator, we put the difference between two sample means minus d0, and d0 is the value of the difference between population mean 1 and population mean 2 specified in the null hypothesis. So when we will be testing equal population means, d0 will be equal to 0. So in other words, d0 is the hypothetical difference between two population means specified in the null hypothesis. And then we divide this difference by the square root out of sigma 1 squared over n1 plus sigma 2 squared over n2. However, as we already know, we almost never know the true population variances. Therefore, as before, we will approximate them with sample variances. So instead of having sigma 1 and sigma 2, we will have s1 and s2. And that leaves us with the following possibilities. So negative tail test, positive tail test, and two-tail test. If you look at the null hypothesis of these three tests, you will see that they are identical, that the true difference in the population means is equal to d0. And as for the alternative hypothesis, in case of the negative tail test, it will be that the difference is lower than d0. In case of the positive tail test, the alternative hypothesis will specify that the difference in the population means is higher than d0. And as for the two-tail test, the alternative hypothesis is that the difference is not equal to d0. And the rejection rule is the same as in case of one sample. So for the negative tail test, we reject the null when the estimated z-score is below the critical value, the negative z-score at level alpha. As for the positive tail test, we reject the null when the estimated z-score is above the critical z-score at level alpha. And as for the two-tail test, the null hypothesis is rejected when the estimated z-score in absolute terms is higher than the critical z-score at the level alpha over 2. We can also use the p-value to make a conclusion about the rejection and non-rejection of the null hypothesis. And we reject the null hypothesis when the p-value is lower than the significance level of alpha. Speaking of significance levels, let's have a quick revision of the critical values. So when alpha is equal to 10, so when the significance level is specified to be 10, the critical z-score for the negative tail test is negative 1.28. For the positive tail test, that would be 1.28. And as for the two-tail test, that would be 10% divided by 2. So the z-score at 5%, which is 1.645. As for the significance level of 5%, the critical z-score for the negative tail test is negative 1.645. For the positive tail test, that would be positive 1.645. And as for the two-tail test, the critical z-score will be the value at the significance level of 5 divided by 2, so at 2.5%, which is 1.96. And as for the significance level of 1%, the critical z-score in case of the negative tail test is negative 2.33. In case of the positive tail test, that would be positive 2.33. And as for the two-tail test, that would be the z-score at 1 divided by 2, so 0.5%, which is 2.575.